record. We're looking at variance this week, which is really, if we look at the learning objectives, we're comparing certain factors, certain test results, which you can read about in chapter 13, which are measures of variance. And we're not going to spend a lot of time on that, although you probably should read it, because quite frankly, it doesn't appear in your final. So why, you know, I'm not sure that we're going to have a whole lot, but it's a way of, we'll pull it up and look at it, but it's a way of looking at variance when we have different sets of data. But we're going to look at the linear correlation coefficient, which is pretty straightforward. If we go over to, go back to one of these things here, and hold on, I'm told that my internet connection is unstable. I'm using my phone hotspot for this. It shouldn't be a problem. No, it shouldn't be. So we'll just pretend that this is not an issue. The correlation coefficient really involves two sets of data. And we looked at that last week with a correlation coefficient. So what we want to do is just do that calculation here. So we're going to put this correlation coefficient in, which is Correl, okay? And we are looking at two arrays of data. And so we will put those two in. And then do the calculation. So the correlation coefficient of these two sets of data, which we have no idea what they are, but the correlation is 0.63. And if we go back to the textbook, let me bring this up as part of the share. Trying to remember to do that. I'm going to go back up to chapter 12. Which was correlation. And let's do, we'll go there. And remember the correlation coefficient, there were some rules. The correlation coefficient, let's get down to where they're talking about that. When we calculate our correlation coefficient, what we're doing is calculating how well the variation in data for two arrays of data, how similar that variation is. So there is actually some, and we talked about using, you know, calculating the equation for a straight line, the y-intercept and the slope, that would correspond to that data set, the scatter plot. Okay, so if the slope is positive, in other words, going up from left to right, then we have a positive correlation. If it's negative, going down, it's a negative correlation. That's just a descriptor. It has nothing, there's no value assigned to whether it's positive or negative, right? All we're doing is looking at what the, if they are correlated at all. And of course, a horizontal line is no correlation. So what we have to do when we calculate a correlation coefficient is actually square that correlation and take a look at the value. And there's we got to this the other day. We got to this the other day. And if we square that correlation, then it gives us the a measure of how of cause of being able to say, okay, and our correlation coefficient when we did that a minute ago, our correlation coefficient was 0.635. And I'm just going to pull up my calculator. I won't bother to I won't bother you with showing it to you. Squaring that is 0.403. So basically that says that between these two sets of data, and I'll call them back up again. Where was it? Oh. Doesn't like that. It doesn't like that. Why is that? Okay. So I'll have to call it up a different way. Okay, we'll do the share. Okay. So what we're saying is that the square of the correlation coefficient was 0.403. That means that 40.3% of the variation in Y can be related to the variation in X. This is why we go back now. Let's go back to the text. Okay, if we go back here to the text, when we're looking at this, we saw a table here, right, that relates the correlation coefficient to how significant it is. Okay, so in this case, minus 6.32 to plus 6.32. And if we remember from the plot, it was 0.635 before. So that's going to be outside this range. And so it is significant. So this is sort of a rule of thumb, looking at whether or not there is a significant correlation between two data sets. Does that make sense?
Yeah.
Okay. This on page 694 is worth remembering. Okay. So anything less than, anything between minus 6.32 and plus 6.32 is considered not significant. Okay. Does that make sense?
Mhm.
Okay, so what it basically says is that the slope of your line has to be fairly significant. So that's really what it is. Now, you're not going to be asked to do that, but let's take a look at some of these tests. And let's go to chapter 13. I just want to touch briefly on analysis of variance. Your text is kind of clunky. Okay, so what we're going to be looking at is just what we call a one-way, and ANOVA is just an acronym for analysis of variance. That's all. It looks like a crazy word that has some weird meaning, but that's all it is. So all we have is looking at group means. So if we're looking at a set of data, let's get to that, that are taken out of several samples of a population, then and looking across data as well, across populations, there are several assumptions. Number one is that we've done a good selection process and the population is assumed to be what we call normal, which is to say it is a group that, it's a population that represents a good scattering of the defined population. Meaning if you were doing the difference between, say, men and women, you wouldn't include any men in the women's group, right? That makes sense. That's a pretty obvious example, but what it has to is they all have to be within the needs of the study. They have to be uniform. And here, if we're talking about looking at the difference between groups of men and groups of women, then we then would want to further define are there any other restrictions like ages or occupations. You know, some of the studies that are done about the difference between the pay of women and men in occupations, they would have to be looking at women and men doing the same job. And you would not want to be looking at people working, say, in the same field, but doing very different jobs. Let's go to just the legal field. There's a very great difference between the pay to a legal assistant and the pay to a lawyer, right? So what you would want to do is say, okay, is there a big difference between male legal assistant salaries and female legal assistant salaries? Then you've got a group that's pretty uniform. You don't care, you may want to further stratify it by years of experience, say. But you would define your group and so the population would be uniform and then randomly selected. And there is an assumption in the one-way test that if we looked at the populations, we're assuming that they have essentially equal standard deviations. And remember, they say variance is here. Variance is just the square of the standard deviation. So if the variances, if the standard deviations are approximately equal, then the variances will be. So if we look at a group where we have very similar sets of people here, and roughly the same mean. The means don't have to be exactly equal, but roughly the same mean. And that's what this, remember the box plot, the boundary between Q2 and Q3 is actually the median. And the median and the mean are, of course, different. But when we're looking at this, we would be looking at the mean here would be very similar. But here we've got groups where there is significant non-overlap. There's a lot of overlap, but there's also significant differences. So we have a different definition here. That is what we call the alternative hypothesis. At least one pair of means is different. So here we can see that this mean and this mean are very different, but this mean and this mean are not, and there's not much difference between these. So if we look at that with the, if the means are not true, then we really can't say that the differences between these groups, and this is the purpose of this, the difference here comes from random variation. There are going to be differences. And it depends on how you select. If you're looking at, say, the mean salaries for female legal assistants in northern Colorado, it's liable to be different from that in central Alabama. Hopefully higher, which is not right either, but nonetheless, you know, we would hope that people living here are getting paid more because it costs a lot more. And Alabama is still a relatively cheap place to live. For how long? Who knows? But nonetheless, we've got, you know, we want to be sure that we are looking at these. So, so there's one of the issues with looking at this analysis of variance is, okay, if we have these different groups that do not have very similar means, at least one pair of those groups are not equal. Whereas in this, we're assuming that these approximately equal each other. So the mean of group 1, group 2, group 3, up to group K. And remember, the mu is a population mean. Let's go down another page. What we call F distribution is, we haven't done t-tests. And that's not part of this class, but that's another way of looking at the validity of our data. There's a lot of calculations here, but we can look at the way these things are calculated a couple of ways. And these terms, MS, etc. Let's get some definitions here. Oh, come off it. Why is that not stable? Maybe it's all the rain we're having. MS means mean square, which is to say the mean of all the squares in the sample that represent the variations among the samples. So what we're looking at here is a way of examining our data to see if since we've chosen theoretically the same population of subjects, if the statistical data can actually be compared. A lot of times people will compare statistical data that are really not comparable. One of them being exactly this thing we had up on the other page here, where theoretically these are the same population, but we have very different data, obviously. So this would make us go back and examine our study, really. But the variance, the F ratio is a fraction, and that it really is a mathematical tool used by our statisticians. So two variance estimates are made, which is the variance between samples. Okay, so we have the variance of between these samples, which is also when we can weight it if the sample sizes are significantly different as well. And then variance within samples as sort of what we call pooled variance, which is to say that we pool the data from within our sample and base our calculations on that. And again, this variation can be, if there's a tremendous amount of variations within samples, then what it's sort of like the outlier stuff that we talked about last week, something that is significantly outside the bulk of the data. And that can be unexplained, or we may find that it's an error. So what we do is from that is we can carry out a series of calculations that we won't be doing in this class. But the idea of these kinds of tests is part of the detailed work of descriptive statistics, examining the ability to compare groups of data. This kind of analysis is used a lot in medicine. And possibly, I can see some places possibly in the automotive industry as well, where you have clinical trials. In medicine, you have clinical trials on a specific drug, but there are several trials and they're slightly different. Maybe the populations are slightly different. Maybe the dosing schedule is slightly different. We can find ways of pooling those data in something we call meta-analysis. Meta-analysis is a means of looking at data from slightly differently designed studies. If they're very differently designed, you can't do it. But I remember one of the most famous of these was a meta-analysis of a number of studies of different antidepressant drugs in the class known as selective serotonin reuptake inhibitors, the Prozac and so forth family of drugs. So in this case, the studies were pretty much alike, but the drugs were different. They worked the same way. Their doses, effective doses were different. But what they did was they studied 85,000 patients in all these studies. So a lot of data. They pooled all that data and did these kinds of tests to make sure that they were able to do it. And then they found out, to the absolute rage of the pharmaceutical industry, that about 80% of the effectiveness of these drugs was because of placebo, which implies to most people that the drugs basically don't work. And in fact, there are a lot of people who believe that. In reality, you know, for a person who's highly depressed, they don't care if it's placebo or drug. All they know is they feel better. And that's the purpose of the drug. So the pharmaceutical industry went berserk, and I thought to myself, you guys are nuts. You should be saying, so the patients get better, who cares? But they made a big deal out of it. anyway, and that kind of meta-analysis is common in medicine. I can easily see it looking across failure rates, say, of different components of automobiles manufactured by the same company, or maybe failure rates, looking at failure rates in different companies. But seeing if, but I was thinking about different components manufactured by the same operation as a means of correlating, seeing if there are general problems with the manufacturer as opposed to the specific products. So that's just one thing I thought of. There are some things in here that I think you really you won't be using them in the final, but I wanted you to know that we have lots of ways of using these methods. Here's one that is a real popular thing these days: diet plans tested for mean weight loss. We talked about statistical significance versus practical significance with respect to the Atkins diet early on in this class. Remember that?
Yeah.
Yeah. The fact is that statistically, very significant data said that these people would lose an average of 5 pounds in a year. But practically speaking, you know, who cares? You can lose 5 pounds in a week if you want. So, you know, what difference does it make? So here we go for 3 different diet plans. And we have weight losses per plan. So we've got these different groups, these different samples, plan 1, plan 2, and plan 3. And in plan 1, we have actually 4 results from people. And obviously this is, it doesn't matter if this is pounds or kilos. Of course, if it's kilos, it's a little more significant. But these are obviously weight losses. And these, we have different sample sizes, excuse me. So we figured out the standard deviations for each one, or I mean the, which one is this? Oh, the sum of each one. So the sum here is, excuse me, 15. The sum here is 16 and a half, and this is 15 and a half. So we divide those by the squares, and we weight them. So the squares get put together, and then we pool them. So these calculations, we won't go through the rationale here, but you can see that these calculations start getting complicated, right? What we've got is a way of doing this. Now they've used a calculator here. And so what we've done is we've come up with an F-test of 0.3769. So what does that mean? So let's go back up. We calculate that, and I believe that indicates that these are not very well related. The total weight loss was roughly the same, so that is the sum. The average is the mean is going to be the same, 4.1 and 5 and a little over 5. So they're not all that different. So all of these tests just tell us that we have these values that we can calculate that tell us how significant these results are. So, and the F formula here, let's see, is telling us that the groups themselves are acceptable. You know, these are very small groups, so mostly we wouldn't call those an acceptable sample size. But the F test is designed to help us understand that just how close to one, if indeed we have a good group. In other words, the means are about the same, the F ratio should approximate 1. And in reality, by approximating 1, they mean, you know, it's much closer to 1 than 0. So our F test here says that the results, let's go back up here a way, the results are pretty much pretty much equal across there. In other words, there's almost no difference between those 3 plans. Does that make sense? Okay. So had there been a big difference, we might have seen that. So let's go back to wake up. Our week 4. All right. So the discussion this week is looking at correlation and causality. Just because 2 things happen at once doesn't mean they cause each other. I mean, there are some things that are very obvious. You know, your truck got hit and that caused it to get damaged, right? That is a correlation.
Yeah.
Those are directly related. However, if your battery had failed, you probably couldn't relate that to being hit. It might have happened and you couldn't start your car or something, and you got hit because you weren't moving and somebody ran into you, but the actual cause, they happen basically simultaneously. One of the biggest areas is right now in vaccination, in medicine, where people are claiming that some of the vaccines cause autism. And it's based on a not unreasonable question to ask, which is, my child got vaccinated and a week later started showing signs of autism. It is not unreasonable to ask if they're related at all. And this is, but a lot of statistical analysis has gone in. I mean, we're talking about statistical analysis on populations of millions of people have shown that there is no direct relationship between the 2. So that's one area, and it's still an area of controversy because, quite frankly, as a parent, if that happened to one of my kids, I'd definitely say, is this related? I would want to know. And I would be hard pressed to say, you know, okay, it isn't. But again, I'd have to see the data. So the issue, a lot of times, it goes back to the subway fares and pizza slice prices in New York. They happen at the same time. Um, you know, big deal. Um, we've just we see this a lot, um, where people look at something and say, well, this happened at the same time, therefore it must be related. Well, the answer is that the world is not made up of either or. There are many other factors that you would have to take into consideration. So statistical analysis can help us pinpoint those examples where there is a very direct relationship. If we cannot find a third or fourth or 12th cause or whatever. With the pizza slices and the subway fares, of course, inflation is the driving factor behind that. But there are many times when things just happen, and they happen simultaneously, and we have to be careful of that. So that's what this example. So here's a couple of other examples. For example, you find, get off there. You find a correlation between the number of hours you watch TV and your GPA. The more you watch TV, the lower your GPA that term. In this case, watching TV did not really cause your GPA to drop. It was the fact that you weren't doing your studies. It didn't matter if you were playing video games or indulging in your hobby of driving race cars, and I mention that because my son-in-law films those things. So they're related. My daughter just spent today driving a Porsche in Australia on a track at 175 kilometers an hour, which I figured was about 110 miles an hour. So yeah, she says, "Come on down. I'll get you in the Porsche." And I thought, I'll do that because I have driven a lot.
That sounds fun.
Oh yeah, yeah. She's actually done a couple of tracks, but cool. Nonetheless, it's whatever you're doing. Watching television does not cause you to do that. But on the other hand, if you go to looking at things like sedentary jobs and people gaining weight, there is you can't say that the job makes you gain weight, but if it's a sedentary job, if you're sitting at a desk all day, you're not burning calories moving. So in that case, you're not getting enough exercise. There's the cause, but it's easy to say, oh, that person must have a desk job because they're overweight. Well, no. It might not have anything to do with a desk job. In fact, he might be a person that has a standing desk and is always on his feet. So it is the lack of exercise, the lack of burning calories, and at the same time, not reducing caloric intake. Because that's the other thing, people who are, one of the reasons that ex-athletes start gaining weight is because all of a sudden they're not burning 10,000 calories a day. And they're still eating 3 pounds of steak. Right?
Yeah.
So it's a case of looking at what causes what. Okay. And asking yourself always, is this a reasonable question? It's always good to say, okay, this happened. Are they related? That puts you on the track of thinking about causality and using correlation to investigate the potential for causality. And in fact, that's what happens when people are looking at why say the car breaks down. A number of years ago, Ralph Nader wrote his book, Unsafe at Any Speed, which was about the Chevy Corvair. And the Corvair was an air-cooled mid-engine vehicle that was actually pretty unstable on the road.
Really?
Pardon?
Air cooled?
Yeah, it was an air-cooled
You
engine.
said air cooled?
Yeah, it was air-cooled. As I recall, that's how it was. It was sort of like the VW Bug, an air-cooled engine. And it was also a mid-mounted engine. So it just wasn't a very good automobile, and there were a lot of accidents and a lot of deaths. But the issue is when you see that, you think, oh, the car is bad. Well, I don't know that the car itself inherently was bad. But perhaps it was just not the right car for the time. Another question to ask is, do people need to have different driving skills with a car that's going to handle aerodynamically different? Which it did. It was a big square boxy thing. It looked like a box. It looked like a candy box on wheels, flat and wide and long on wheels. And it wasn't a very comfortable car to ride in. I ended up riding halfway across the state of New Mexico one time in one, and I thought I was gonna die. I was folded up into a ball in most of the car. It was awful. But we were college kids. We didn't have any money, and so we took the chance. We did it. But so the issue is to look at, you look at something and you say, well, what's going on? You find out maybe that you have a number of automobile accidents in one specific, where the damage is in one specific part of the car. Just say the right front quarter is getting destroyed in an unusually high number, because automobiles are random. And I just saw a mouse run by. Great. Automobiles are random. Yeah, I'm not too happy about that. And so you would think, to yourself, well, what's going on with all these cars that are getting, where the predominant damage is in one specific location on the car? Is there something wrong with the way it handles? Is there something wrong with, say, the visibility, or what? So you would look at this and start asking your questions. And that's one of the basic things about looking at correlation and causality, is to be really hunting for how do we answer and ask and answer the right questions, and look at what's going on. So that's really what we're doing with correlation and causality this week in the discussion. Are you going to back up there? There is no assignment. I know that just stresses you no end. But
That's so weird.
yeah, well, that's just the way it worked out. I don't know why there's no assignment at all, but that's the way they've structured this one. There is, of course, a final assessment. So
my other class doesn't have an assignment either.
yeah, a lot
Do you
of
think
them
it's because of the
don't.
holidays?
No, has nothing to do with the holidays. What's your other class?
Retail marketing with
Ah,
John.
Yeah, yeah. A lot of these 400 level classes don't, 300 and 400 level classes don't seem to have week 4 assignments unless we create them. A lot of times with
Really?
yeah, a lot of times with these upper level classes, we'll what I will do is when there's a lot of reading, I will insert an assignment that sort of forces reading of the text.
Hmm.
I have not done that here, uh, but I really, you know, I look at it
Okay.
and I was looking at trying to at what to do about it the other day, and decided that I wouldn't bother. It just didn't seem like it was worth it. Um,
Oh, well, thank you.
you're welcome. But I do want you to look over the reading material. Um, and if we look at up here the course media for the week, um, we're looking at chapters 9, 12, and 13. 12 is about is a lot about correlation. 9, let's go back and look at the textbook again. Um,
The PDF,
yeah,
these aren't the same. They don't line up, right? I mean, it's chapter 13, chapter 12.
13, 12, and 9 this week. And chapter 9 is hypothesis testing. So we're not actually discussing any of that. However, let's just talk briefly about what we mean about hypothesis testing. Remember we talked about um, the null and alternative hypothesis a few minutes ago. Um, that 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 the null hypothesis is basically there's no difference between sample means and a population mean. In other words, they're the same. The alternative is that the population is is not the same as a sample, or we have smaller samples that do not have the same mean within a population. So hypothesis testing comes, and when that comes out, it means that there's something wrong with our data. Okay.
Okay.
Some the is so we have a couple of things. Let's go up here and look at what this is. If let's see. So we look at these and we look at the standard deviation, or rather, yeah, at the mean in each of these populations, and ask ourselves if the if they're basically the same in a group as a population. The way you find out about a population, quite frankly, is to have enough or a big enough group that you can get a good standard curve. So the um, the 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 null hypothesis would be that the population mean is equal to the same as the sample mean, 8th graders. And that the null hypothesis is that they're not equal. The alternative, rather, is that they're not equal. Let's see if we can and we use these kinds of analyses to actually ask ourselves if our study is valid, if we've um, um, if the um, if we've asked the right questions, if we've gotten the data in a reasonably objective way. So let's keep looking here at what I'm I was looking at this earlier. Okay. So when we are looking at this, we're looking at red tide is a toxin producing algae that shellfish eat. And so in Massachusetts, the Division of Marine Fisheries monitors this with regular sampling, and if the level of toxin in clams, and clams is a huge business in Massachusetts, exceeds 800 micrograms per kilo of clam meat. And so they take a sample of clam meat and they measure the amount that's in there. And we're going to look at the different types of errors here. And we've defined type 1 error, which is making an assumption when that there is, in this particular case, a type 1 error would be assuming that there is toxin in the absence of a red tide. And a red tide, you can see it really literally is a ruddy color in the water. It's really bad along the coasts. Another is to assume that your sample represents the population. Maybe what you've got is a sample of clam, and what you've done is measure, which they can do, the amount of toxin in, say, 10 grams, a third of an ounce of clam meat, because a kilo of clam meat is a lot of clams. So they just take a few clams and process the meat. And they assume that it represents the entire clam population wherever they've been taken from, and they ban the fishing. So that is a type, I think that's a type 2 error. We haven't, we have made an assumption that every group of clams is going to be the same, and they're not necessarily. You can have clams being harvested from, a mile down the coast that have absolutely no toxin. But if you've tested only a couple of clams from a specific area, you're making an assumption. So this is about sampling. So obviously, they should be sampling from a variety of different areas. So looking at our hypothesis, and here the hypothesis is that our hypothesis is that if we find red tide toxin in one small batch of clams in an area, they're going to be in all of them. And that's not necessarily a valid assumption, hypothesis. So we need to examine our our assumptions, our ideas. So let's take a look at cancer cure rates as another example. A certain experimental drug claims a cure rate of at least 75% with prostate cancer. Irrelevant, it's only in males. They don't have to specify that it's in males. So a type 1 error is that the patient believes that the cure rate for the drug is less than 75% when it's at least 75%. So that's an error of assuming the basic results of testing. And another one is whether or not the cancer believes it has a 75% cure rate when it's actually less. And that is an example, again, of what happens with this type 2 is assuming something that isn't true. Assuming that the experimental drug is going to cure his cancer, the drug, they might look at whether or not they'd want to use this drug for treatment. So the type 2 error here, the patient believing that has a very high rate, a higher rate of cure than it really does, leads the patient to want to use the drug and may not respond. The other rate is that the patient doesn't believe it's going to work when it does and refuses treatment. So there are two types of errors that are there. So okay, here's one that assume a null hypothesis. In other words, that the percentage of adults have with jobs is at least 88%. In this particular case, the null hypothesis means that if you took any group of adults, 88 out of 100 approximately would have jobs. So the errors here are to reject or not to reject that hypothesis when it's actually wrong, not to question it. That's one error. That is one of those errors. Not to reject it when not to reject it when the adults have a job that's at least 88% when it's actually at least. This is not an error. Just saw my mouse again.
He's your friend. You got to accept it. So the errors are when they choose to not to reject, not when they reject.
It's when they so here what we want to do is identify the type 1 error and the type 2 error. Here, is it an error to not to reject or to accept the null hypothesis that the percentage of adults is at least with jobs is at least 88% when it's actually less? Well, that's an error. To not
a type 2 error.
It. Pardon? It would be
type 2 error.
I think it's a type 2 error. Yes. And then we have not to reject.
But not.
Yeah. Okay.
But not when they reject it. Like D.
We'll get
is
there.
D not an error?
Right. Let's talk about these sequentially. Okay. Not to reject that null hypothesis, mean accepting it, when that the percentage of adults who have jobs is at least 88%, when it is actually at least that much, that's not an error. You're not rejecting a true value. In this first one, you are rejecting, you are not rejecting a false value. Okay, so the null hypothesis is that the percentage of adults with jobs is at least 88%. If you accept that and it's actually less, that's a type 2 error. So the next one is really not an error, not to reject it when that percentage is actually correct. Then we have reject it when that the percentage who have jobs is at least 88%, when the percentage is at least 88%. That is a type 1 error. So we reject the truth. Okay, this last one, reject the null hypothesis, that is at least, or rather, when who have jobs as at least 88% when it's actually less, that is not an error. If we are rejecting something, a hypothesis that is untrue. Okay, so again, this is going back and looking at your assumptions and your hypotheses. Does that make sense? Okay, yeah. Let's go back now to here. Excuse me. So this week's just this discussion and
yeah,
and the assessment. So do you have any questions?
Nope. I don't think so. Not yet.
Not yet. Okay, that's fair. That's fair. So then let's just cut this off and we'll meet again on Thursday. I should be back in town.
Okay.
Looks like the weather is going to be good for flying out of Washington and then out of Chicago. So I should be back in town.
Oh, good.
So
good. I'm glad to hear it. I definitely, I hope you have safe travels.
Thank you. I'm planning on it. There's my hypothesis. Air travel is safe.
Yes.
So, but I have been on some pretty bumpy rides. I don't expect that now. Okay, so I will see you Thursday evening. Is your car running?
Okay.
Excuse me. Is your truck running yet?
Nope.
Oh.
No, it's gonna cost. I know. It's gonna cost me about $1,000 approximately.
Okay. Insurance gonna cover it or?
Nope. I just had liability because I own the truck. The title's right over there. So.
Well, what about the guy that hit you?
I know. Well, I hit a lady. So my insurance was gonna cover her.
Well, that's good.
Not me. Yeah. But I have to get my license back first. I'll get my license back January 8th, I think. Fingers crossed.
Okay, so you'll miss the first couple of days of the mod.
Yeah. Yeah, hopefully not much more though. I should be back in the swing of things before. Yeah. Do you have my schedule?
I don't, and in
you don't
fact,
have schedules, do you?
I have not been able. I haven't been at school, so email Christy.
Yeah. Okay.
Email Christy.
I'll shoot her an email.
Or Tempest, either one.
See what I can do.
And they'll tell you. And you should be able to get that schedule. but I didn't have access to them because
Okay.
they weren't available before I had to leave town. And they might
That
actually
makes
not be,
sense. Yeah.
they might not actually be available for another week or so
Oh, okay.
because of this funny break.
Yeah, that's not a big deal.
Yeah.
Yeah.
So,
That makes
but you
sense.
can find out. Christy knows what you're scheduled for because I guarantee you you're scheduled. I already have my classes set. So, I mean, I haven't seen my
Yeah.
rosters, but I know that the classes are set, so she has to have students in them. So give her a call.
Yeah.
Okay?
Okay. I'll email her, see if I can get a hold of her.
Super. Well, I'm going to go ahead and stop the recording and turn off the meeting. So hope to see you on campus sometime soon, Jessica.
Yeah.
It's
Me
been a
too.
weird
Thank you
mod.
so much. I appreciate
Yeah.
your help.
By
Yeah,
the
it
way,
has been.
I don't know if you heard, but Kyle's mom passed away yesterday. You know
I did.
Kyle?
I texted Allie
Okay.
to wish her condolences and
Yeah.
Kyle condolences. Yeah,
Great.
very, very sad.
Yeah. It's a tough time of the year to lose someone, believe me.
Yeah. Yeah, it can't be
So,
easy. I
yep.
know.
So, at any rate, I will see you on campus. We'll talk again Thursday evening. So
Okay.
I'll
Awesome.
plan on
I'll
a
be
course.
here.
Okay, great. So we'll plan on
Okay.
talking at 6, okay?
Okay.
All right.
Awesome.
I'll set up a Zoom
Thank you,
session
Mike.
for 6.
I
You bet,
appreciate it.
Jessica. Talk to you later.
Mm-hmm.
Okay.
Talk
Bye-bye
to you
now.
later.